The human brain is a bit like your grandmother's attic, full of mysterious relics, faint memories, and, if you're not careful, some very dusty cobwebs. But unlike attics, aging brains don't just accumulate harmless nostalgia. They accumulate senescent glial cells, non-neuronal support cells that, when they grow old and cranky, may be quietly sabotaging neural function. Fortunately, a new generation of machine learning tools is helping us comb through the brain's cellular clutter to find out exactly which of these senescent cells are causing problems, which might be innocent bystanders, and which could actually be trying to help. It's neurobiology meets CSI, but with more equations and fewer sunglasses. First, a refresher. Glial cells are the brain's unsung heroes, or at least, its very busy support staff. They outnumber neurons by a factor of 10 in some regions and perform everything from nutrient delivery and waste cleanup to immune surveillance and synaptic maintenance. But just like overworked interns who have been left on the job for too long without a break, some glial cells start to burn out. These senescent glia don't die, and instead pump out inflammatory and neurotoxic factors that can turn a harmonious neural neighborhood into a chronic low-grade war zone. This neuroinflammatory storm is now being implicated in everything from cognitive decline to full-blown neurodegenerative disease. Here's where things get mind-bending, in both the literal and computational sense. Glial senescence isn't just one thing. Microglia, the brain's immune cells, astrocytes, the star-shaped multitaskers, and oligodendrocyte progenitors, the cells that help insulate neurons, can all go senescent. But they do it differently in different places at different stages of disease. One senescent astrocyte subtype might be linked to tau tangles and Alzheimer's, while another type of microglial senescence might be more involved in Parkinson's dopamine neuron loss. It's not a single villain. It's a cast of poorly aging characters with different quirks, and until recently, we couldn't really tell them apart. Enter machine learning, the digital Sherlock Holmes of cellular biology. Thanks to advanced neural networks, image segmentation algorithms, and multiomics integration, researchers are now able to map cellular senescence in the brain with ridiculous granularity. We're talking spatial transcriptomics combined with AI-enhanced brain imaging that can pinpoint not just where senescent glia are hiding, but what they're saying at the molecular level. Think of it as eavesdropping on every angry cell in the brain and organizing them by how much damage they're doing, how inflammatory they are, and which disease they seem to be nudging along. One of the big wins here is early diagnosis. By training machine learning models on PET scans and MRI data tagged with senescence-related molecular signatures, scientists are developing tools that can detect early glial dysfunction before symptoms even show up. That's like catching Alzheimer's 10 years before the first memory lapse, or spotting Parkinson's in the preclinical phase when motor symptoms haven't even emerged. And because these models can differentiate between glial subtypes and their unique senescence flavor, they open up doors for tailored, cell-type-specific interventions. It's personalized medicine for your brain's cleaning crew, and the excitement doesn't stop there. The AI isn't just identifying the bad actors, it's helping to design the hit list. Once we know which glial subtypes are driving neurodegeneration, we can start developing senolytics or xenomorphics that either eliminate them or tame their inflammatory ways. That's not just symptom management, it's disease modification at the cellular level. Imagine a drug that crosses the blood-brain barrier and selectively silences only the angry microglia whispering "kill neurons" into the ether, while sparing their more helpful cousins still cleaning up plaques or pruning synapses. Thanks to machine learning, that dream is closer to a blueprint than a fantasy. But it gets even nerdier. AI models are now exploring how senescent glia interact with each other and with neurons over time, creating dynamic maps of aging brain ecosystems. It's a bit like tracking the slow breakdown of a city's infrastructure. Some parts collapse quickly, others adapt, and some unexpected heroes emerge. The models even allow simulations. What happens if you remove senescent astrocytes in the hippocampus? Does memory improve? What if you boost oligodendrocyte turnover in the substantia nigra? Does motor coordination stabilize? These are questions we can now test in silico before ever touching a mouse or a human brain. Of course, there are still hurdles. Brain tissue is complex, imaging resolution has limits, and senescence markers can be slippery. Not all glial cells waving the molecular "I'm old" flag are necessarily harmful. Some may be performing anti-inflammatory or tissue protective roles. Others might be stuck in temporary quiescence or responding to injury in a helpful way. Machine learning can spot patterns, But distinguishing causation from correlation, especially in a network as tangled as the brain, still takes careful validation and a healthy dose of skepticism. Still, the fact that we can now discuss glial senescent subtypes as if they were menu options is a scientific miracle. We've gone from seeing aging as an inevitable blur of decline to understanding it as a set of programmable, mappable cellular states, each with its own fingerprint and, potentially, its own off switch. Machine learning didn't just give us better data. It gave us a new lens to see the brain not as a static, crumbling cathedral, but as a rewritable, improvable, still very much alive system. In the future, treating neurodegenerative diseases may not be about saving neurons at all. It may be about cleaning up the overgrown glial jungle surrounding them. And with AI as our machete, we're finally hacking a path toward clearer thinking, longer memory, and maybe even a few more good decades with the attic lights on.